it's my honor to speak here, and I'm really appreciate the support from NIH because it's the NIH's effort that motivated me to do some technology development in metabolomics. And now today I'm going to talk about some of the research results, also whatever we have done at the Pacific Northwest National Laboratory, and report it to you and listen to your feedback. Yeah, so I will start from here. So the talk is about the high-resolution MR metabolomics on biological tissues and live objects. The reason we do metabolomics on tissues is because from many of the disease and it's tissue and organ specific, and if you would imagine if you directly profile the tissue, and it may give you some direct evidence about the disease progression and how the metabolite are related to the specific disease. So about the MR metabolomics, so we have traditional MR metabolomics, that's the solution MR metabolomics, probably about 90% of the scientists in the field of MR metabolomics, they devote their effort to the traditional liquid state MR metabolomics. We also have a high resolution magic angle spinning MR metabolomics on intact tissues. So in this way, you do not have to do tissue metabolite extraction process. Of course, in order to do MR metabolomics, you have to pull over the biostatistics to find out the discriminatory metabolites. Then after you get the discriminatory metabolite, you have to have bioinformatics to look at the metabolite pathway and the networks to say how these things related to the biology. There is another branch of very important metabolomics, that's the metabolomic flux measurement used in isotope enriched carbon-13. In this way, you can trace out with some kind of starting metabolite to say how they migrate to different other metabolites to trace out the detailed pathway. So I will go through first use a case-guided introduction to solution. That's a traditional MR metabolomics. That's what have been done. So in my group, just use it as an example to walk through the process. So in order to get the metabolomics done for MR on tissue samples, for the traditional metabolomics, so first we have to do sample extraction. Then second step is to do MR profiling on the extracts. The third step, we do statistical analysis. The fourth step is to do the pathway analysis. For the sample extraction process, actually this step it's by far the most important step. If you do not get this step right, and the follow-up, very labor-intensive steps might all get wrong. So you have to be really careful about not to introduce systematic errors in the tissue extraction process. So there are a couple of ways you can do the extraction. First, you can for soft tissue, and you can easily need to homogenize it. And for bones and other hard materials like skins, so there is a way you can use freeze meal. This is liquid nitrogen. So you put your sample in liquid in the container and soak in the liquid nitrogen, then you have a way to mill it. So that's the machine we do the milling. So that's a protocol. So how we get the do the extractions. So it's basically following the standard protocol from Jerry Nicholson's group, John Linden's group. That's Nature Protocols, and published here. Everybody knows this one, and people follow this one closely nowadays. It's the protocol recommended. And then, so that's what we do based on the different, based on the available sample tissues and the materials, like what's the way to use different extraction. It's the same extraction protocols, but it just scales to different ratios so that you can work on a range of tissue weight. So it's simple to follow. After you get the tissue extracts, then you have to resuspend it in the MR solvents, then do the conventional solution MR metabolomics. So that's here is the ways, and that's the standard MR protocols. So you can follow to do this kind of metabolomics. Then once you put it in the MR machine, actually MR is very reliable. It's quantitative, and you simultaneous profile metabolites without discrimination to say which one you get more scaling factor or not. You get everything profiled quantitatively. And for this case is so we work on spleen. So this spleen from the mouse is we intentionally injected the tumor cell into the legs of the mouse, that it develop into the cancer, and it's a skin cancer that it migrate into the different organ of the mouse. In this case, it's the spleen. So we can profile spleen with the traditional MR metabolomics. We can simultaneously detect about 73 metabolites from the aqueous soluble metabolites. So the concentration in the tissue can go down to about micromolar concentration. The MR is knowing that we have a sensitivity problem, but the advantage is we can simultaneously detect and amino acids and lipids and sugars and some other simple acids like lactate acid and etc. So it's a very quantitative and reliable method. If you get the extraction process right, and the MR can be 95% or more repeatable every time, regardless of how you do it. If you do it, whether you are a new user or a very experienced user, and the MR itself is very reliable. But the unreliable factor comes from whether you do your extraction process right. So if you get your spectral, then you need to do the biostatistics. There are ways, basic way is to do principal component analysis. On top of it, you need to be more complex is POS, and further is OPOS. So you can get you can buy you can buy commercial software and do this kind of analysis. They are relatively simple, and there are many free software also available from NIH website, and you can do like a principal component as a PRX. So the principal component analysis, it's a mother of all statistical methods. It's the most simple one. It's unsupervised methods, meaning you don't have to know the sample from diseased or from the controlled group, and it will classify it as groups. If you can see the difference, it will automatically show it. Then it goes to partial least square, that's a POS analysis. This one, and it's a little bit more complex than principal component analysis, and so it's a linear regression method. So this one, and you do need to know and to put some like a control, you assign it to 0, and the disease you assign it to 1. So you know which sample comes from which. You eliminate one variable and makes the data presentation a little bit nicer. And for the OPOS is one step further, and you eliminate some systematic errors such as like spectrometry and base the systematic errors. That's orthogonal to the variable variations, meaning if you have disease versus control, that shows some difference. If something is orthogonal to these directions, this one can fill it out. So this one shows, and we do, so it's a way to do OPO analysis. And so the controlled, you show blue, and the tumor, so that's a melanoma group, will show blue, also show green. So this is the bind data, and so this one, we feed the bind data, we feed the spectral, we get the metabolite information, use kilometrics methods. If we use kilometrics methods, we exactly know, like for this system, 73 metabolites. We know the concentration because we have internal standard put in the solvents. Then we can directly analyze this 73 metabolites. We know which one gets increased, which one gets decreased. And then the statistical tool will differentiate between them. So in this case, you have nice separation. Of course, this is we know it's a diseased case, so it is separated widely. So it's a very successful case. And for the lipids, we can also show the OPS plot, and it shows some of the things gets elevated or decreased. So that's the metabolites we found from this case. They show statistical increase or decrease. And then because we know which metabolite gets the concentration increase or decrease, then you can go to the go into website that's about bioinformatics. Basically, it's the pathway network analysis. So plug in your metabolites and then look at it to say, and the metabolite correspond to which metabolic pathway that gets changed. So that's we found. So you have a bunch of pathways, component metabolite gets elevated or decreased related to different pathway. And for the EMMA metabolomics, and before we tightly integrate with biologists, so that's a place we can go. So we end up here for the profiling. Then further step would be to say how this one, how it is important related to biology. Then you can do the transcriminals, and for other system of biology, so biology should all collaborate together to get some very meaningful results. But for EMMA metabolic profiling, and so that's how far we can go. Then the second topic I'm going to talk about is if we do not do extraction, we can directly profile in the tissue. Because this is one of the places you can go to the clinics when the doctor is operating a patient. You do not have much time. Maybe you have at the most 10 minutes and to analyze the results. So you want to obtain the results within that short time. One way to do it, you directly put the tissue into the Metabolomics spinning rotor. So that's a rotor, and it is spinning. you may need a few minutes to put the tissue in the rotor, and you quickly spin the sample inside the magnet at an angle. We call it a magic angle 54.7 degrees because of that angle, and collapse the white line into high resolution spectral. So that's what you can get. I get this example from this Nature Protocol paper. And when you compare and this one with the water soluble and the lipid soluble, if you do the extraction, and they are remarkably similar, but here you eliminate the extraction process, so you get the results within like maybe half an hour, maybe 15 minutes if you are experienced. For Magellan spinning, another way, if you want to look at a very tiny sample, because some of the disease may be finished with a few cells, like with very small tissues. For very small tissues, the cell type is very homogeneous. So there are ways to do very small sample volume. So this one is from Signor's group, and in Nature, publishing in Nature. So this is one way you can go to less than 1 microliter of sample, but you still have to spin very fast. And for the regular traditional Magellan spinning, if you spin very fast and you destroy the cells, so meaning if you do it in a long periods of time, and the sample itself will change. So and then in my group, we try to do Magellan spinning, but we don't want to destroy the tissue structure. We spin it very slowly. So they have an advantage. When you spin the tissue slowly, it's easy to keep the tissue and sealed inside the spinning rotor. And if you want to spin the sample very fast, how to seal the sample cell is pretty challenging inside the strong magnet. So spin slow has this kind of advantage. It's easy to do. Also, if you spin a tissue sample slowly, and you can put a big chunk of tissue to do the spinning experiment, so you can work with a range of sample tissue from very small to very big. So we have two approaches. One is we spin sufficiently slow, but it's slow, but it's still kind of not viable for the biological object, live biological objects such as a laboratory animal like laboratory mice. Then, so this one I'm going to talk later. But so for now, I'm going to talk about approach 2. That's we use ultra slow Magellan spinning. So this is a method we rotate the sample in a strong magnetic field only at a speed of 1 to 6 hertz. Because if you rotate this sufficiently slow, and you will not damage the objects, because you can you can think for a ski for the people's skin and on the eyes, you can rotate about a few hertz, meaning 1 second you can rotate a few times without a big problem. So this is how we do very slow Magellan spinning to get a high resolution MR spectral. So we put a mouse inside a rotating probe and let it rotate in a magnetic field. So this you have lots of technology development about the pulse sequence development, because MR is it's a very good example of quantum system, meaning you can use quantum mechanics to apply to work on this system and to manipulate the spin of the nucleus and let it eliminate some of the broadening and get a high resolution spectrum. So they are very sophisticated pulse sequence development, but the consequence is we are able to get the high resolution MR spectrum. If we just do the traditional MR metabolomics on a static tissue sample, you do not have much spectral resolution. That's here. If we rotate it, in this case is a couple of 1 Hertz, we can get a significantly enhanced spectral resolution that shows lipids and sugar signal already. Then we can further, because it spins so slow, we can put a mouse and inside the spinner and rotate it to 1.5 Hertz to the Mageia spinning. We can look at the metabolites. So that's a rotation mechanism, how to rotate the mouse inside the strong magnet. So this one just shows what kind of enhanced spectral resolution enhancement we can get from this kind of experiment. Without the rotating, that's what you get. You do not have much information. When you rotate it at 1.5 Hertz, so you get enhanced spectral resolution. So you get the lipids, you get some sugar signal, you get some choline signal here. So remember, this is a live laboratory mouse. Then we can also incorporate the localized spectroscopy into this experiment and then look at a specific organ inside a live object. So in order to do localized spectroscopy, we put a pulse field gradient on top of the pulse sequence. So that's the way we do the pulse gradient synchronized with the pulse sequence. So it's a very complex process, but it works. So this is an example showing we have a piece of phantom sample. We put carrots inside the silicon gel. So for this one, the silicon sealant inside a piece of carrots, we wanted to pick up a signal from the carrots. If we do not do localized spectroscopy, so that's we get this huge water signal. And if we do localized spectroscopy in this range, we pick up the silicon sealant signal. So the method works. And then we apply to a live mouse. So we want to focus on the liver. So we get the liver spectral. So that we compare it to slow manual spinning. They have similarities, just not as good as if we spin like 100 Hertz. The 1.5 Hertz compared to 100 Hertz, not as good as that, but we still get a significant enhanced spectral resolution on a live object. Yeah, so that's the summary for this ultra-slow Mageia spinning. So the take-home message is, and by manipulating the pulse sequence and do very slow Mageia spinning, in a way do not introduce destructive force to the object, we can get a reasonable high spectral resolution from anywhere inside the live object. So that's for the slow mass. Then further, and since if you continually rotate in one direction, if you do it slowly, you can feel dizzy, and you're in your head. Then we think about we rotate back and forth. So we build a probe and rotate the specimen, and one time clockwise and followed by anti-clockwise. In this way, we can eliminate the centrifuge effects and to cause it damage, some potential damage to the brain. So that's a mechanism to make it rotate. So that's a pulse sequence to do this kind of experiments. We slowly ramp it up. We rotate it about 1 rot period. Then at the end we slow it down. We reverse the rotation. So it works. We use solid sample because in solid sample the spectral line width is the most broad. So we use this as example to illustrate the methods. And this is whatever you get in solid on a static sample. This is you do the rotate back and forth. We get significantly enhances spectral resolution. So we haven't applied this method to the biological tissue yet, but I imagine it would work. So since rotating the sample and rotating the magnetic field, they are equivalent in terms of fundamental physics. My collaborator from MIT, so actually based on our slow medium spinning results, and they are developing a rotating magnet, MR rotating magnet. In this way, they rotate by rotating the magnet itself, they rotate the magnetic field instead of rotating the sample or the biological objects. So this is all to completely eliminate the centrifuge effects from the rotation. They get their almost phase 1 project done, looking for their proposed phase 2 project to fully realize the rotating magnet concept. So as for this, I wanted to conclude my presentation. So this is people involved in this project. I really appreciate the grants support from NIH and also from some other funding agencies. So thank you for your attention. I'm be very happy to answer any questions you have. Yeah.
Thank you for taking my question. My name is Scott Rose. I'm a student at Rowan SOM. So thank you for taking my question. My name is Scott Gross, and I'm a student at Rowan SOM. I just had a question about the NMR. Do impurities ever cloud the NMR readings or the peaks, such as if there's impurities from the metabolites that are made in the process of cancer forming?
Impurities, you mean, right?
Yeah, impurities like. Does it ever get cloudy, like things mixed together, such as if a diabetic went into ketoacidosis and ketones started to form, and the ketones let off other metabolites, which could cloud the ketones that were produced in the process?
So that's a great question. So when we do the traditional metabolomics on tissues, we use the methanol chloroform extraction procedure. And when you use that procedure, so you have the aqueous phase, soluble metabolites, and the lipids, soluble metabolites, they separate into 2 layers. Then we connect the lipids layer and also connect the aqueous soluble layer separately. Then sometimes if you do not do it very carefully, and they will have the lipids layer and little bit liquid into the aqueous soluble layer. So you will have contaminations from the liquid lipids layer. But usually you will be able to recognize those metabolites in the spectral. So you can, when you do the analysis, you can consider that effects. Then there is also a chance if you store the sample, because after the extraction, for example, for the aqueous layer, so we have to dry the sample, evaporate the solvents. And then we get the powders. The powders we will save it in the -80 before the experiments. And during this, so this process is fine. But when you resuspend the metabolite into the MR solvents, if you store it in the ambient condition for too long, in particular for the lipids, they are going to degrade. So you cannot save for too long. They degrade. We can usually say degradations. So it's better you do it fast enough. If you want to keep the sample, you refreeze it in the refrigerator. So metabolite may change if you do not kill the enzymes completely. Has this answered your question?
Yes,
Thank you. Yeah.
One question. For your spin technology, what is the status in clinic? Has it been in clinic or is coming?
The spinning technology, one thing that can be applied, go in the direction to the clinicals is for the not too slow, but reasonably slow, like we spin 40 hertz to about 200 hertz. So that's not very fast as well. So this technology, the sensitivity is really high, and we can work on range of sample tissues from less than 1 micrometer and to like a few hundred milligram of tissue samples. So that one has some, will be some value to the clinical applications. Yeah.
A question. Talking about Yan, Dalhousie University of Canada.
Mm.
So with the mice, with your trials with the mice I'm assuming are anesthetized?
Yeah.
How long are they anesthetized for?
For the spinning experiment, and we anesthetize the mouse because this MRI experiment is a two-dimensional MRI experiment, and we need about 1 hour to finish the experiment. So the mouse will be anesthetized inside the magnet for about 1 hour.
So is there any concern of the anesthesia impacting the profile of the metabolites?
Yeah, could be.
Yeah.
We have not yet explored this factor yet. So the mouse and the sleeps inside the magnet obviously for too long.
Yeah.
So that's why, and my MIT collaborate, they try to not rotate the sample, they try to just rotate the magnet. You don't have to anesthetize object. It's still for animal, yes, because if you don't do it, the protocol, we cannot go through the protocol.
Run away,
Yeah, the wrong way.
I know it's safe.